This is a session on statistics and survey methods. Our first speaker, Dr. Terril Hurst, has worked at Raytheon since 2005 with a focus on rigorous methods for developing and using modeling and simulation resources. He teaches several courses, including Johns Hopkins and Raytheon course, Incredible Modeling and Simulation, and internal courses for DASE, Bayesian Networks, and Bayesian Analysis. Terril has attended and contributed regularly for 15 years to DATAWorks, CASD, and ACAS. Prior to joining Raytheon, Dr. Hurst worked for 27 years at Hewlett-Packard Laboratories on developing and testing computer data storage devices and distributed systems. He obtained all his degrees at Brigham Young University and completed a post-doctoral appointment in artificial intelligence at Stanford University. Please help me welcome Dr. Hurst.
Thank you. As was said, my name is Terril Hurst from Raytheon. I'd like to first of all acknowledge my co-authors here who have really been very instrumental in laying out how we get the work done that I've tried to define for us. Doctors Kevin Rotz and David Anderson and Adam Berryman. We've authored several publications together, including a paper on adaptive sampling, Bayesian adaptive sampling that we presented 2 years ago here at DataWorks. I put this build test fix icon. As was said, I used to work at Hewlett-Packard, and the co-founder of Hewlett-Packard, David Packard, was really insistent on following the concept of negative feedback control. So you can adjust whether it's at a company level or a circuit level in a servo system. And so that is going to play a big part of my message today, is how we're closing that loop at multiple levels. And what we're presenting is a Bayesian approach for credible simulation, development, and usage. So in my time at Raytheon, I have pioneered the usage and application of three checklists. They're really protocols. We call them modeling, simulation, analysis. It doesn't mean like gauge R&R. I know this is the audience that measurement system analysis might come to mind, but MSA here means something particular. When I presented this paper at SciTech last year, there were a lot of pilots in the audience, and I pointed out to them that you could fit these checklists on a knee board. No matter how much fancy digital stuff you have in a cockpit, most pilots still have a knee board Velcro strapped to their knee so they can communicate clearly with air traffic control and get home safely. And so we have these very high level protocols that we have developed. And in a Venn diagram notion, we have this picture here. 2 years ago, when we presented our paper here, the theme of that conference was risk-informed decision-making. As was mentioned, I teach a course with Simone Youngblood from Johns Hopkins, and she lets me use this balance scale at the bottom left here, where you have a scale between risk and resources. And it is always a balancing act between the cost of knowing something versus the risk of assuming and moving on when you make a decision. And that is very, very true in MSA. And so these protocols help us to do that and get alignment as a group of MSA stakeholders. And so over the years, we've published several papers on these protocols. The MDR protocol stands for Model, Description, and Report. This, you'll notice, includes several crucial stakeholder reviews as we move forward from intended use of a modeling and sim to V&V plans and then results. And then we gain acceptance that we're going to trust that simulation. And so that intersects then in the form of a modeling and simulation query that we're going to ask using what we call DASE, Design and Analysis of Simulation Experiments. And then when we both develop the simulation and use it, we've brought in most recently the three-step Bayesian analysis protocol. This protocol was not developed at Raytheon. We teach courses, Andrew Gelman, if you've read his book, Bayesian Data Analysis, he's very clear on this three-step protocol. Just because you invoke Bayes' theorem doesn't mean you're Bayesian. You have to follow this protocol rigorously. And this is really the focus of this talk. We're going to show in the limited time we have here a brief example of calibrating, a very simple example of calibrating a simulation. And we maintain that Bayesian analysis is key for moving from frequentist DASE, DOE, it's kind of sometimes seen as isolation, not by the statisticians who know this thing, but so much as by practitioners who say, well, just give me the recipe and I'll design an experiment. It's not the statisticians who are the challenge, it's people who statisticians are trying to teach. But when it comes to simulation experiments, we have to move to the fully integrated, credible modeling, simulation, and evaluation. That's how we transform MSA into a credible digital test and evaluation venue. When I was doing research for this paper, I discovered this figure here. There's a buzzword. Before, the buzzword of digital engineering was the buzzword of simulation-based acquisition. And this picture is extracted from guidelines from the Director of Test and Evaluation and the Director of Systems Engineering and Evaluation in December 1997. And so it showed the kind of grand big idea to be able to do, they didn't call it build, test, fix, they called it simulate, integrate, and analyze, test. The build was kind of left out of that. If you read the paper, well, the hope was that there's all this money that could be saved by the DoD and time by using cheap, some people think it's free, modeling and simulation resources rather than the number of expensive field test events. That was the hope. The reality in those decades when Moore's law was kicking in and decades of replacing expensive field tests with cheaper modeling sim and using what have now become very large and still expensive high performance computing facilities, then you have a reduced amount of simuland data. Now, simuland is a fancy word that VV&A people use for that which is being simulated, because we talk about the word systems gets ambiguous sometimes. So when I say simuland, I mean the thing being tested. So the available data for validating, calibrating that has much reduced. It also has resulted in more difficulty in making sure that the sim is credible for its intended use. And then there's also a high risk of sim or HPC misuse. So the truth is, no matter how much HPC you have and you're throwing sims at a problem, if you still have limited field data, you have to be honest about the uncertainty that's present in your simulation. And so I like to draw dashed yellow lines here between simulation testing on their diagram and analysis to imply this permeability that we're trying to get through Bayesian analysis, to kind of break down that wall between, oh, that's test and oh, that's simulation. They need each other badly. Again, I'm not going to read this whole quote, but here's the longer quote from Packard. When I was entering college, Packard took a leave of absence from HP. He became Undersecretary of Defense to Melvin Laird. And if you read the history, Nixon had tried to invite him into the administration, but he said no. But he said yes to Laird. He came in and he developed what were called the Packard's Law Rules of Acquisition. And Secretary of Air Force Frank Kendall, in a blog that he posted in 2013 when he was the Undersecretary of Acquisition, commented on David Packard's Rules of Acquisition that he published in 1971 as Undersecretary of State. And then more recently, as Air Force Secretary, he's commented on what he called the overhyped digital engineering. That might upset some people, but we maintain that credible MSA is really the key for calibrating the expectations on the payoff that we could get from digital engineering. If you don't have trust in your simulations, it's all just buzzwords and talking at each other. So how do we do that? I'm going to show an extremely simple example. Now, this Bayesian analysis methodology, as those of you who practice it know, the mathematics scales way beyond this pretty much toy example I'm going to demonstrate here. The problem, though, is as that scale goes up, you have limited test data that becomes a bigger and bigger challenge, and we'll illustrate that in this example. We're going to try to close the loop, calibrate a simulation. So we have a notional example, notional data here, a solid rocket motor simulation. This simulation has 5 knobs that we can turn for calibrating that rocket motor model. Things like the burn rate of the solid rocket propellant, other things that you can imagine in a rocket motor that we don't have the time to go into. Now, the response of interest when you're designing a solid rocket motor, you want thrust or specific impulse. The thing you don't want is so much pressure that you explode the vessel, okay? But those, unfortunately, as you can see from this relationship here, they go up directly with each other. So we did a designed experiment here. We did 500 Latin hypercube samples of points in this calibration space, and that's what you see in those green dots. And of that 500 Latin hypercube samples, the one that gave us the smallest calibration error, this essentially was a square root of sum of squareds function of the field data we had, which are those designated by those X's with the simulation, that gave us that little red triangle there. So, but you can see there's this huge region when you independently, randomly draw those values of those calibration factors. Well, can we do better than that? And what we did to do better than that is we applied Bayesian analysis to build a model, a posterior probability distribution across those 5 calibration factors. In this case, we looked at several models. We use, by the way, STAN. Those of you are familiar with STAN for Markov chain Monte Carlo. But in this case, we decided we were given no information on the measurement error of the test data. So we built a multivariate normal distribution, but we did not know the mean or the covariance of that. If you think conjugate priors, then there is a distribution I had never heard of until Dr. Ross brought to my attention called the normal inverse Wishart. As a conjugate prior, when you have a multivariate normal distribution, you can apply that and you don't have to use Markov chain Monte Carlo, you have a posterior distribution. So given the limited data that we had, that prior was felt to be adequate. And when we do that, then those 500 points collapse to a set of a joint probability distribution that gives you this streak of blue points here that nicely encapsulates the test data that we have. So we had very limited test data. We had not that limited 500 Latin hypercube sample points. And so we were using those together in this joint probability distribution that we're using. Now, once we calibrated the simulation, then we got to work, said, okay, let's do a design optimization problem. The objective is this: we wish to choose a nozzle exit area, A sub 0. We want to maximize specific impulse, but we want to do it with a low probability of exceeding that maximum expected operating pressure. So we set that at 1%. And doing that and running the model that we had with, ignore the one on the right, I will talk to the zoom in of this, but just focus on the left plot for a moment. First of all, the uncalibrated curve, we have a thing called probability of non-compliance. That's just that probability that we exceed our max expected operating pressure. As you sweep through values, design variable of nozzle exit area, you see that that probability of non-compliance kind of ambles down from high values that you wouldn't want to be designing to a lower value. And you're giving up specific impulse as you do it. Contrast that with the blue curve with its 95% credible envelope. You see this almost like more like a step function on a scale, right? So it's very clear when you're the regimes between, you wouldn't want to be designing with your rocket nozzle area here. Let's design it down below. Now let's move to the zoom in of those two things. In this case, we had a constraint of 1%. That's this horizontal line here. And if you go to the edge of the 95% credible envelope for the uncalibrated, it says, well, we better limit our exit area to 0.8 in arbitrary units. Whereas if we do with the posterior, well, we can cut it down to 0.7 and still have confidence that we're not going to exceed that constraint. Now, this does not always happen. Sometimes it's the reverse of these two. In other words, you don't always get a better answer with a calibrated sim, unfortunately. but you always get a surer answer when you're making a decision because you have quantified the uncertainty. So I hope that example kind of gives a feel. We do this at much greater scale every day on simulations to calibrate those. So this picture on the right is a picture that we use in our Bayesian analysis class that we teach. There's this maximum likelihood estimate point, which is a point estimate. But then those of you who are familiar with the terminology of Bayesian analysis, we have these broader areas, the posterior predictive distribution is the broadest, where you are fully quantifying and estimating all of the uncertainty that you have. So here in 2016, at the predecessor to this conference, we published a paper on what we call the DASE axioms. At that point, we were just dutifully trying to follow traditional design of experiments concepts in tests to be simulation experiments. But in the last few years, we've evolved to this Bayesian analysis methodology, and it has really enabled us to transform, for example, from doing a priori samples to fully decision theoretic adaptive sampling. And this example we showed you it shows how you can blend that test data with your simulation data and scientific tested analysis techniques. I feel like this, as far as MSA goes, it really, this integrated MSA that we're using with Bayesian methods is equivalent to transitioning from just practicing this fairly narrow area of DOE to full scientific test analysis techniques generally. So thank you. Appreciate your time.